With merge sort is a good opportunity to take a look at the intrinsic difficulty of the sorting problem. That's called complexity, and we'll look at that next. The idea of complexity is it's a framework for studying the efficiency of all the algorithms for solving a particular problem. That's called computational complexity. And in order to do this sensibly, we need what's called a model of computation, the operations that the algorithms are allowed to perform. For sorting, that's kind of straightforward. What we're going to do is have a cost model where we count the comparisons. Now, in framing the difficulty of problems, we'll need two things. One is what's called an upper bound, which is a cost guarantee that's provided by some algorithm for solving the problem. That's an upper bound on how difficult it is to solve the problem. We have an algorithm that can solve it. It's at least that easy. And then we also look for a lower bound, which is a limit on the cost guarantee of all algorithms. No algorithm can do better. Now what we seek ideally is what's called an optimal algorithm, where we prove that the upper bound and the lower bound are the same. That's an algorithm that we know that has the best possible cost guarantee. That's the ideal for solving any problem. So for sorting, let's look at what each of these are. The model of computation is what's called a decision tree. What that means is that all we can use is compares. That's the only way we can access the data. So our cost model is the number of compares. Merge sort provides an upper bound. That's an algorithm that's guaranteed to get the sort done in time proportional to n log n. And what we'll look at now is the lower bound. There's a trivial lower bound which says you have to look at all the data. That's n. And we'll look at a better lower bound and see that merge sort is optimal. So here's the basic idea for proving a lower bound for sorting. Let's say we have three different items, A, B, and C. Whatever algorithm we have is going to first do a comparison between two of the items. Let's say they're A and B. And then there's two cases. Either it's yes or it's not yes. Let's say they're distinct. And there'll be some code between the compares, but either way, then there's going to be a different compare. If A is less than B, maybe the next compare is B against C. And if you find that B is less than C and A is less than B, then you know that they're in any algorithm that does that knows that the items are in the order A, B, C. If B less than C goes the other way, then it takes another comparison to determine the order. In this case, if C is less than B and A is less than C, then those three compares show that the order has to be A, C, B. And if C is less than A, then it's got to be C, A, B. Those three compares that C is less than A, C is less than B, and A is less than B. The only possibility is C, A, B. And continuing on the right, perhaps the next compare is A less than C, and maybe if C is less than A, another compare B less than C. So in this case, if you go from top to bottom in the tree, with three compares at most, you can determine the ordering of the three different items. The idea of the lower bound generalizes this argument to figure out the number of compares that you need for a minimum to determine the ordering among n items. Now, the height of the tree, as I just mentioned, is the worst case number of compares. Out of all the orderings, the one that's furthest down in the tree, that's the worst case. And so the algorithm, no matter what the input is, the tree tells us a bound on the number of compares taken by the algorithm. And there's got to be at least one leaf for each possible ordering. If there's some ordering that is not appear in a tree corresponding to a particular algorithm, then that algorithm can't sort, can't tell the difference between two different orderings. So the lower bound is a proposition that uses a decision tree like that to prove that any compare-based sorting algorithm has to use at least log base 2 of n factorial compares in the worst case. And by Stirling's approximation, we know that log base 2 of n factorial is proportional to n log base 2n. And then the proof is generalizes what I talked about in the decision tree on the last slide. We assume that the array consists of n distinct values, and there's a decision tree that describes the performance of any algorithm, the compare sequence done by any algorithm to determine the n factorial different orderings. So this tree has to have at least n factorial leaves. And if the tree is of height h, it has at most 2 to the h leaves. The tree that has the most leaves of height h is totally complete, and that one has 2 to the h leaves. And those observations give us the lower bound. 2 to the h has to be greater than or equal to the number of leaves, and the number of leaves has to be greater than or equal to n factorial, so that implies the height of the tree has to be greater than or equal to log base 2 of n factorial, which is proportional to n log n by Stirling's formula. That's a lower bound on the complexity of sorting. So we knew that the upper bound was proportional to n log n, and we just proved that the lower bound is proportional to n log n, and that means that merge sort is an optimal algorithm. That's the first goal of algorithm design, is to try and find optimal algorithms for the problems that we need to solve. Now, you have to take these results in context. Really, what we proved is that merge sort is optimal with respect to number compares, but we already know that it's not optimal with respect to space usage. Merge sort uses twice as extra space proportional to the size of the array it has to sort. And simple algorithms like insertion sort don't. They don't use any extra space at all. So what we want to take from these theoretical results is a guide when we're looking at implementations and trying to solve practical problems. In this example, what the theory tells us is, don't try to design a sorting algorithm that guarantees to use substantially fewer compares than merge sort. Say half n log n compares. Is there a method that uses half log n compares? The lower bound says no. And that's a very useful thing, because otherwise we might try to define such an algorithm. On the other hand, maybe there is an algorithm that uses n log n compares and also uses optimal space. It's optimal with respect to both space and time, and that's what we're going to look at soon. The other thing is that the lower bound is for the particular model of computation being studied, in this case compares. It might not hold if the algorithm has more information about the keys. For example, if it's known that the input is almost ordered. We saw that insertion sort can be linear time for files that are almost ordered. Or something about the distribution of key values. If there are a lot of equal keys, we can get it sorted faster than in n log n. And maybe the way the keys are represented, we'll look at different methods that take advantage of such properties. So partially ordered arrays, we may not need n log n compares. Duplicate keys, we may not need n log n compares. We're going to look at a method that gets that done in linear time in a lot of situations. And later on, we'll look at digital properties of keys where we can use digit or character compares instead of whole key compares and get a faster sort for certain practical applications. Computational complexity is a very useful way to help us understand properties of algorithms and help guide our design decisions.